Welcome to this introduction to what makes metadata good metadata by SDSC, GoFair US and partners. This video is hosted by the NIH Office of Data Science and Emerging Technologies and GoFair US. So, what makes metadata good metadata? In the evolution towards high-quality metadata, we typically start with the basics. Unstructured text files, like a simple README, located in the same directory as the data. These files provide the initial context needed to describe what the data is, but because they lack structure, they remain dark to machines. Our goal is to move this vital context out of these isolated text files and into a machine-readable format. Moving one step further in the evolution, we encounter metadata as tabular information. Here, context is organized into clear property value pairs, often stored in a spreadsheet or a CSV file within the same directory. This is a significant upgrade. By separating the name of a property from its value, we make it much easier for a human to scan the parameters of a data set at a glance. The next level of maturity is reached when we stop typing free-form values and start reusing entries from controlled lists. In this stage, a researcher might pull standardized terms from a data codebook. By selecting values from a list, rather than creating them from scratch, we ensure that the metadata is consistent and predictable. Now the evolution reaches a critical turning point. Beyond just using controlled lists, we begin reusing published global vocabularies for our metadata values. By mapping our data descriptions to terms maintained by a recognized community, we ensure that our data is no longer speaking a local dialect, but a shared language that can be understood by researchers and systems. Here we aren't just using published vocabularies. We are ensuring that every entity, both the data itself and the terms used to describe it, is anchored by a persistent identifier or PID. By using PIDs like DOIs or persistent URLs, we create a permanent bridge to the information. This ensures that even if a web address changes or a server moves, the metadata remains resolvable and the F in fair findability is fully realized. A name alone for a person can be ambiguous or shared by others. By adding an ORCID ID, we replace that text string with a unique persistent identifier. This ensures that the work is always correctly attributed to the right person, regardless of name changes, different spellings, or institutional moves. It turns a simple name into a permanent machine-readable link to a researcher's entire professional record. In the evolution to fair metadata, we eventually move beyond identifying the things and start identifying the relationships between them. By using PIDs for object properties, we are assigning persistent identifiers to our predicates. This means that the connection between a data set and the researcher that created it isn't just a label, it's a globally defined link. This way, we allow machines to understand the exact nature of the relationship, enabling the data to be integrated into the global knowledge graph. Let's sum this up and analyze a piece of metadata step by step. Data is the subject we want to further describe. The specific attribute we want to know about it is of which type it is. Dataset is the type we want to assign to it, so the whole sentence reads, "The data is of type dataset." So you can see how data and metadata are related. The data is the subject, metadata is the predicate, and the term I use in the object position of the sentence is part of a vocabulary. For each part of the sentence, we use persistent identifiers. For the predicate, we use object properties as defined in a metadata schema. For the term we use in the object position, we use concepts from a published thesaurus or ontology. Let's have a closer look at one of the key frameworks for good metadata, the FAIR principles and how they are related to good metadata. For F1, metadata should get assigned a globally unique and persistent identifier by using an identifier service. For F2, data should be described with rich metadata based on the metadata schema. According to the F3 principle, it is essential that there is a clear bidirectional relationship between the data and its metadata. This means we must use unique identifiers for both components. By following a formal specification to link these identifiers, we ensure that anyone or any machine who finds the metadata can instantly locate the data and vice versa. Without this explicit link, even the best metadata remains an orphan with no way to verify which data set it actually describes. For F4, metadata should be indexed in a searchable resource, a registry. For making metadata accessible, principle A1.1 requires that the protocol used to retrieve metadata is free, open, and universally implementable. This means that accessing the description of a dataset shouldn't require proprietary software or a paid subscription. Whether it's through a standard web browser or an automated API, the gate to the metadata must be open to everyone, ensuring that technical barriers don't stand in the way of data discovery. While data can be locked behind an authorization service specified in A1.2, metadata should actually be as open as possible. Principle A2 is a commitment to the long-term record of science. It requires that metadata remain accessible even if the data itself is no longer available, perhaps due to storage costs, privacy shifts, or data expiration. This persistence of context must be clearly stated in the registry's metadata preservation policy. To make metadata interoperable, it must use a formal accessible knowledge representation language like RDF, OWL, JSON LD, and use FAIR vocabularies for the values in the object position of the description. For compliance with I3, metadata should use qualified references to other metadata by using object properties from ontologies for the predicates to indicate the specific nature of the relationship. Let's look at a practical user story. Imagine a researcher needing to find and compare datasets involving two specific types of bacteria. Because the original data was annotated using terms from a published controlled vocabulary, the search is seamless. These terms act as universal keywords within a searchable repository, making it easy for others to find, compare, and aggregate data. Instead of guessing which synonyms a previous scientist might have used, the researcher uses the standardized terms with associated definitions published in a vocabulary. Vocabularies help to clarify terms by providing definitions, thus avoiding ambiguity. As we see here, the term culture changes meaning depending on the domain. Without a reference to a specific ontology, a machine cannot distinguish between a biological sample and a social construct. Metadata should be made reusable by assigning an open access license. In addition, metadata should also have detailed provenance metadata, like the author's reference and its publication date. Last but not least, for metadata to be considered good metadata, the record must be complete. According to principles F2 and R1, this means the metadata should be rich. providing not just the title and date, but a full description of the experiment, the equipment used, and the parameters of the study. This richness is what ensures that a future researcher has enough information to truly understand the data and determine if it is fit for their own use. You now have the tools for machine-readable metadata. In the next video, we take it a step further, a comprehensive, step-by-step guide to designing a customized metadata schema.